Hello everybody, my name is Thasso and I am very sorry because I'm going to talk about digital rights management, one of the most exciting and interesting topics that you could imagine. You might wonder why I'm on stage and why I'm talking about DRM in general. The reason for this is that I work for a company called CAS Labs, and there I lead the player team, so I'm not directly involved with our DRM backend, which is the other service that we run is DRM Today, a multi-DRM cloud-based DRM license service. But since I come from the player side, I have, let's say, a lot of experience integrating DRMs into the player on various platforms. And that can be a challenge specifically because DRM is not a super exciting topic. Basically, in most of the cases, it's just an external requirement. It's nothing you want to do. It's something you have to do. It's something that's demanded by you. It could be that this demand comes out of your company. It could be that it comes, and that's most often the case, comes from content owners, from the people who you license your content from. So if you play premium content, then there's a good chance that that you're basically forced to protect that content with DRM. So in the best case, what can happen with DRM is that nobody will notice that you have it, right? So your playback experience will be as if you would not have DRM. That would be the sort of the best case outcome. If somebody knows a use case where DRM actually makes a user experience better, by any means tell me, because I would be very interested in that. One of the challenges with DRM, and that's something that I'm trying to highlight in this talk a little bit, is that in the vast majority of the cases, it will not be enough to deal with just one system. It's not like, okay, there's my DRM thingy, this is how I integrated the player, I'm done. In almost all cases, you deploy on multiple platforms, on multiple browsers, in multiple environments, and that usually requires you to deal with more than one system for your production setup, basically. So what's the whole point of DRM? The main point of DRM is to hide the decryption key, right? So you want to give a license into your player so that your video playback pipeline can actually decrypt protected samples, then decode them and show them on screen. But you don't want to expose that decryption key because potentially you want to take it away from the user again. So it's digital data. Once he has the key, he can decrypt your content and the game is over basically. So that's one of the main things behind DRM. The other that comes with the DRM license is that you want to be able to control the playback environment to a certain degree, right? So for instance, you want to do, let's say, rental licenses. So you want to allow a license to be valid for 48 hours. And the third thing is that you want to control, or the DRM system, let's say, wants to have control over the playback device. So there are certain restrictions, and we talk about them a little bit later, when it comes to the protection level, the amount of security, if you will, that is put on top of the DRM license, and that is hardware and device specific. And so that is something that needs to come out of the DRM system to the DRM backend and then back into the client. And the outcome of this is that DRM can be fun if you sort of try to visualize it nicely, because it gives a kind of non-smiling, smiling face. So on the left-hand side, you see sort of the plain key. So you just have a backend. There sits your AES encryption key. You go there, you transmit it over the wire. It probably goes through HTTPS, so it's kind of hidden when it goes over the network. But in the client, it's visible. It's there. It's not only that the player sees it directly. It's in memory on the box and visible to everybody, basically. For the DRM use case, basically what happens is that we wrap a nice little DRM license bubble around that key. The key in that license is encrypted again, so it's the license request specific to your device, and also the key itself is again, there it starts to get a bit fishy, but it's usually specific to the DRM engine that you are using, and it's not just an AES-128 key. There's usually a little bit more cryptographic power on top of that to sort of keep that key secret. And then, as I said earlier, the DRM license comes with properties and device-specific information that is sort of within that bubble. So how does it look like when you actually integrate that into your player? Like the most simple use case that you could imagine basically starts on the upper left corner with your player. So you start loading your content, then the player says, oh, this content is protected. I need a DRM license. Usually with that event, you get handed over what's called Init Data. So that's a piece of information that we need to initialize the DRM engine and trigger a license request. So that's then exactly what happens in the next stage. The CDM, the DRM engine, takes that Init Data, can generate a license request for you. You send that over the wire. The response comes back from your DRM server, and then you take it and feed it back into the CDM, which is the update. I call it update here because that's how it is called in EMI, in the web. And at that point, your player should realize, okay, now I have a decryption key for that specific content, so I can start playback, and everything should be good. So that's the good part of DRM. And that's it, that's the good part. Like, if that works, you can be fairly happy. That works in most of the cases because this is sort of the simple workflow. It's also relatively agnostic to the DRM itself. In most of the cases, it works exactly like that. There are some specific technical details for specific DRMs, but that's usually the workflow that goes through. And there are a couple of things that can go wrong here, but if you can go from the left to the right, there's a chance that your content will play. Let's go through the things that are involved in that workflow. So as I already said, the initialization data is a piece of data that we need to feed to the DRM system, to the CDM, to initialize it, specifically to get the license request out of the DRM system. The Init Data, there are basically two places where this could be located. Either it's in the MP4 init segment. There's a box structure, there's a UUID box, and then under that there's the PSSH box, and in that box is the DRM-specific initialization data. And the alternative to that, at least in Dash and in Dash, is the content protection element, where it's basically posted in your manifest. So the content protection element sits just in your manifest XML. It is specific to the DRM. You can have multiple of them. So if you use multiple DRMs, which you probably will, you have multiple content protection entries, and they basically contain the initialization data. As I said, it's CDM specific. So CDM is your actual DRM engine, and the data there is specific to that DRM engine. So if you're using Whitewine on a Chrome browser, you have specific Whitewine DRM init data. It's specific, but it's not hidden. So you can read that, basically. For Whitewine, it's basically a protocol buffer, and the spec for that is published. So you can just take those bytes and read them and look what's inside. The same is true for PlayReady. It's a piece of XML encoded in little endian 16-bit strings something. So a little bit of a weird encoding, but it's there, it's readable. There's one approach that is new in draft right now on the W3C, which is called the Common Encryption Initialization Data Format. The idea behind that is to sort of unify that, because what's usually in this CDM, in this Init Data segment, is something that identifies the key that you're requesting, which is called the key ID, and then maybe something about the CDM itself. But basically, it's just sort of, I need a license key for this track, and that's what's in the Init Data. So the draft spec basically formalizes that and tries to give sort of a common format so that we can get rid of this CDM-specific Init Data, but instead have sort of one common format that we can all rely on, and that all DRM engines will potentially at some point support. So that's one of the things that where things are moving into sort of a more common direction. So, the DRM license that you get back from your license server after you send your request is, as I described earlier, so I'll keep this one short. The decryption key, it contains properties that are specific to your CDM and specific to the license that you requested. So for instance, if you have requested a rental license that expires in 48 hours. That piece of information is somewhere in that DRM license. If you permit the device to store that license, that is a flag that is sort of inside that license. And in addition, device capability requirements are inside that license. That's important because this is how sort of the DRM backend informs the CDM that certain security restrictions need to be implemented before playback is actually allowed to start. And we look into these in a little bit more detail later. So the last piece of the game in this context is the content decryption module, so the CDM. That is the actual DRM engine. That is your Whitewine or your PlayReady or your Fairplay or your Marlin or your OMA or your Verimatrix engine or your, you name it. The most commonly used CDMs today are Whitewine, PlayReady, and Fairplay. There are others, as I just mentioned. It's debatable. I would consider them legacy. I mean, with these three, you can probably reach like 95% of your users. They're spread over devices and platforms. So if you use Google's Whitewine, you reach people who use Chrome. You reach people who use Firefox, Opera. Everybody on Android supports Whitewine, and maybe a couple of other places. Just to sort of extend on that, there is a Whitewine iOS SDK, so you can deploy Whitewine on iOS, but you lose security capabilities in that sense. PlayReady is from Microsoft, so hence it runs on all the Microsoft browsers. It runs on a lot of consoles, so PlayStation, Xbox, they all support PlayReady. It also runs on Android TV, which is interesting, because the Android TV specification basically says that a proper Android TV implementation needs to support both Whitewine and Android. It doesn't say anything about the security levels that need to be supported by those DRMs on Android TV, but it has interesting sort of side effects that fall out of this. And that's why multi-DRM is also a thing. The example here, for me, is always Amazon's Fire TV platform, because on Fire TV, they basically allow you to use one DRM session for a media track. So they tell you basically that you can do encrypted video and use the one DRM PlayReady in that case, because that's the hardware protected one, to decrypt your video track, but you can't use audio with that same PlayReady DRM session. But of course, you want to protect your audio track as well, right? So now that you are on Android TV and you have a multi-DRM environment, what you can actually do is you can spawn a second DRM session and use Whitewine and just fetch a Whitewine license for your audio track. And why that is possible is because of the way that you're going to encrypt your content, and assuming you use common encryption for that, which is also something that we go into a little bit more detail later. So the last one that is on the slide here is Fairplay, and that basically covers all Apple devices, including Safari on iOS devices since, I think, a year or so now. It's deployed. The CDM, or the DRM engine, sometimes called the key system, is referred to by usually two things. If you're in the browser environment and you use EME, so encrypted media extensions, you refer to it by name, so that's something like com.whitewine.alpha, then that's what you use to basically get a key session for that specific DRM engine. On other platforms, such as Android, they are typically referred to by UUID. And that is conceptually exactly the same, so they are just equivalent. The main purpose from sort of a developer's perspective, where you use the CDM, is generating payloads. So that's what we discussed earlier, when you actually take your init data and then you have to ask your DRM backend for a license. That request, that payload that you send over, you can't just manually construct that. That is something that is given to you by the CDM. The reason for this is that this request and the license that comes back is device specific. So what the CDM does when you generate payload for that license request is it actually puts device-specific information, so device certificates, usually a public key to do some encryption for that DRM license, but also device capabilities into that payload, so that the DRM backend can then use that information to do a sort of an informed decision if it wants to hand you a DRM license or not, or what the capabilities of the requesting device are. And the last point, obviously, is when you receive a license, that's sort of your target. That's the update. That's once you got the license, you need to push it down to the CDM and then load the license into that. The other capabilities of the CDM that are usually not, like you don't necessarily always interface with them, but unfortunately sometimes you have to, is the entire sort of security model around your DRM system. So this part is not very nicely specified, and everybody does a little bit whatever, well, they call it whatever they want. So in the EME specification, there are 5 security levels ranging from 1 being the lowest to 5 being the most secure environment. On Whitewine, it's reversed. There are 3, and Whitewine level 1 is the most secure one, while Whitewine level 3 is the software implementation. And on PlayReady, they call it PlayReady 2000, 3000, 4000, because why not? It's not really clear what implication that has on hardware security. I mean, there are ideas. So typically, PlayReady 3000. So if you ask your device what's your security level and it responds with I'm an SL3000 device, that should give you hardware protection. If it says I'm SL2000, that probably means you don't have hardware protection but only software protection, but not in all cases. So there are some devices that just say, yeah, I'm SL2000, but actually I'm hardware protected. So if you know that, you can do sort of a decision in terms of what license you deliver and what content you can actually play on that device based on the device itself rather than the security level that is exposed by the device. The last piece, and that's where the whole sort of security level hardware, software, decryption becomes interesting, is what I refer to as the secure media pass. So this is something that in browsers is often very much hidden from you because the MSE and EME in the background do sort of the right thing. But on platforms such as Android or, well, basically everywhere where you interface directly with the decoder and you have DRM as a sort of a sidetrack that you need to manually sort of merge those two together, it's a little bit more prominent. And what happens there is that there's a differentiation between what's called a secure decoder and a secure surface. So I use Android as an example here. What happens if you start DRM playback on Android is that you create a decoder, but if you need secure playback, so hardware protection, you need to find the secure decoder. It's relatively easy to find because on Android the decoders have names and the secure ones end in .secure. That's basically the filter that you're applying there. The surface is then sort of the counterpart, right? So now you have a secure decoder which goes hand in hand with the CDM, and it needs to render to the screen. But it doesn't, so you don't want to go through your standard video buffer to expose sort of decoded frames, but instead you want to try to go to the screen directly. And that's what's called sort of the secure surface. On Android, there is actually a class for that, the surface view, that implements that. It exposes the surface and you can pass that down and then the engine can render into that. It has downsides because basically what happens is it punches a hole into the screen and then tries to render directly into that screen buffer. But that means that it will sort of it will make it hard for you to do animations and stuff like that on top of that sort of surface view. So the main point of the secure media pass is to basically make sure that decrypted samples, the decryption key, and the decoded frames are never exposed. So in a hardware-protected environment, this is actually implemented in hardware, hence the name. And these properties are never exposed into memory. Okay, so how to get there? I mentioned earlier already that you can, in EME, you can request the CDM instance, the key session, through the EME APIs, and that is a nice abstraction around different DRM systems. So in the browser, you typically work against EME, and that basically gives you an abstraction on top of the actual DRM that you're using. On Android, you have a similar situation. There's sort of a class structure underneath media DRM that allows you to abstract the underlying CDM instance. The problem with those abstractions is that very quickly you realize that the actual CDM leaks through. So it starts by the request, so you instantiate that thing. So at that point, you already need to tell it exactly which CDM you are actually interested in. So you need to tell it, please give me a key session of the type com white wine alpha to get a white wine key session. But then if you start requesting properties out of that key session, these properties are CDM specific as well. So you ask for the security level, and then you might get the EMI one, but you might on Android not. There's no EMI on Android, obviously, so you get the SL2000s versus the white wine level 1, 2, or 3. And that means that even though it's a nice abstraction around your DRM engine, you still need to do specific codes for the actual DRM in use. So let's start to play some video and see sort of the impact of this. So obviously, let's say, in a common Dash use case, you start with a manifest. So you download your manifest, you parse your manifest, it points to the init segment, so you need to download your init segment. Your ABR already made some smart decision which video rendition you want to play, so it will also start downloading video and audio segments. And at the same time now, because you don't need to necessarily wait for the init segment, you can already start initializing your CDM early, because as I said at the beginning, the init data is part of the manifest, so you know that it's protected content, and you know the CDM initialization data even before you load the init segment into your engine, so you don't need to wait for an event, which means you can start downloading the DRM license. The problem here is that, and that's something that I would like to point out, especially because we had this interesting talk before about playback metrics, that this is a metric that you might be interested in, because this could literally affect the playback start time of your video. If your DRM license request takes 2 seconds, it doesn't matter if you can get all your video segments already up and fill 60 seconds of video buffer, because you have no decryption key, so you can't render the first frame. So this is sort of crucial when it comes to actual time to first frame. And this is something to consider there. What you can do to speed up the playback start time when DRM is involved are a couple of things. The easy one, but obviously this only works when you actually start playback at the beginning of a piece of content, is you can do a clear key start. So simply speaking, well, literally speaking, the first 10 seconds of your video are just in clear. There's no key required for that. So now you have a 10-second window in which you can fetch a DRM license, feed it to the engine, and then once you hit that 10-second boundary, encrypted content starts, and the DRM engine is hopefully sort of warmed up and has the license to play that. Another one that is relatively new, so this was, for instance, introduced in white wine, I think with Chrome 58, is server certificates. So this is something where the DRM engine actually wants to identify the DRM server. It needs to load a certificate for that, and you can do this up front. There's an API for that in EMI, and there's an API for that on Android, and you can load server certificates up front. Those certificates typically don't change. You want to have something in place to have a sort of a fallback in case it did change, but it's something that you can cache and you can load early to avoid an additional request, because what happens if you don't is that the white wine engine will actually trigger 2 events, and you will ask for a license 2 times, where the first one is actually just a payload of 2 bytes, which indicates to the DRM backend that you are actually requesting the server certificate. So you get that back, it loads it, and then you will get another event that says, well, I still have no key, so please load a key. So you do another cycle towards your DRM backend to actually fetch that key. So this is easy to spot. So in Chrome, just open DevTools. If you start playing content and you see 2 requests towards your white wine backend, and the first one has a payload of only 2 bytes, that means you're not caching your server certificate. And this is something that, again, is easy to do, and it saves you 1 round trip to the DRM server. Another thing that you can do if you are allowed to do that, and your platform supports it, is persistent licenses. So on some platforms, not the browser, well, typically not the browser, you can store the license on the device, which means you can literally just take the init data from a random manifest or sideload them somehow, load the license onto the device, and you're ready to go, and you can just have them on the device ready. And the last one is something I would like to expand a little bit on, is bulk license requests. So the idea here is not to load a lot of license for multiple pieces of content, but instead to load multiple license keys for one piece of content, because what typically happens is that when you encrypt your content, you're going to use multiple encryption keys for different tracks. So audio, SD, HD has different tracks, which means if you are not prepared for that, your player will literally do multiple license requests, one for each track that you're intended to play. You can prevent that or try to work around that. It's a little bit DRM backend specific, so you might need to have some logic in your backend to actually group things together, but you can deliver multiple licenses with one request. The trick here is that on the player side, you then need a way to sort of map back from the license that you just loaded onto the tracks that you see in the manifest to make sure that you have what you need to play your tracks. So let's look a little bit at the actual content preparation part. On the left-hand side is something I just wanted to highlight because I've seen that in the real world. Please don't do this. The thing you want to use called common encryption is because it should be common. You want one key or one set of keys for your content, and that key should be shared across multiple DRM environments. So you don't want to package your content specifically for Whitewine, specifically for Play Ready, and specifically for Fair Play, in quotes, because for Fair Play you will have to, but that's a different story. So try to implement it like it's posted on the right-hand side. You want one key, and you want to share that key across your DRM environments. It's possible. Common encryption is exactly why this is possible, and you should try to do it like that. As I said earlier, it's possible, but you still need to deal with multiple keys. The reason for this is that you want to separate audio and video tracks. In this case, in this example, I separated audio, SD, and HD because you might have sort of restrictions where you want to separate SD from HD content as well. But the important message here is please, please, please make sure that you separate audio from video. Because, as I mentioned earlier, there is this secure black box that exists for video. It does not exist for audio. So on the vast majority of platforms, there is no secure audio decoder, which means your audio keys can much easier leak through. So if I'm an attacker, I don't care about your video. I would target your audio track because it's probably easier to reach the key because it doesn't have that secure sort of sandbox within that device. So the work around that is make sure that you use different keys for video and audio, so that even if the audio key leaks through, your video is not decryptable. Okay, this is then what you can do with this. So you have multiple keys. They're mapped by their key ID, so they identify the actual encryption key. You have SD, HD, audio, and then you can group them into sets. This could be manifests, right? So you could just have two manifests, one with the SD audio track and the other one with all three tracks. But it could also be some grouping that happens on the backend side of things. What happened while we sort of used that key to do the encryption is that we used an actual encryption algorithm. And this is something that is new in the DRM space, relatively new, is that it's not that new. There are multiple encryption schemes used forever. You have counter mode, so IES 128 CTR and blockchaining CBC. The reason why you have that is probably just because you can, and I'm not a cryptographer, and probably the cryptographers in the audience will now start yelling at me because no, CBC is better, no, CTR is better. But the outcome of this is that you have duplicated content. The reason for the duplication is that as of today, that's probably what most of you guys are doing in production. You use CTR for Dash and Play Ready, for Whitewine and Play Ready if you do Dash or smooth streaming, and you use CBC for Fair Play when you do HLS. That's just the reality. What's new is that CBC is landed in Whitewine. So there is CBC support in Whitewine. It's implemented in Chrome 68 and above. And it's on Android 7.1 and above. I looked this up on Friday for the fragmentation numbers, so that's not even half of the Android population, if you will, right? So, but if you're happy to just sort of serve half of the people who have an Android phone, you can use CBC today. Unfortunately, that's it with CBC for Whitewine. That's the current state of the art. It's not yet in Firefox. I'm sure they are working on it. It's not anywhere else yet, but maybe it will be coming. PlayReady, similar story. It's in PlayReady 4.0, so you need that on the backend, you need that on the client. It's supposed to be deployed on Xbox already. We tried very hard, and we're still trying very hard. So far, it's not playing, but Microsoft really ensures us that it's there and it should work. So we do probably something wrong, but yeah, it's coming. The problem with this is it's hard to figure it out. Today, it's relatively easy, right? If you're on an Apple device, it's CTR, it's your HLS playlist. If not, it's the other method, and use Dash, and everything is good. With those sort of mixture of modes, things become more tricky. One of the problems is that the common encryption spec doesn't sort of restrict the algorithm in use for the actual encryption. The other problem is, at the moment, there's no capabilities API to query for that. There is work happening on that, specifically on the media capabilities, and it's hopefully going to get in there as well, so that you can query your device, but it's not there today. There will be no legacy support, right? So your 3-year-old, I don't know, Samsung TV will probably never be able to start decrypting CBC. It's just what it is. It will not go backwards. So the path to using CBC for everything is, like, we started working on that, but it will be a long walk. Like, you can expect a couple of years before we have sort of one single content library. Okay, so this is just sort of I wanted to make this text even longer, but I got bored in between. So this basically highlights why you need to use DRM. This is sort of a common thing. You go to your content owner, and they tell you, well, yes, you can play full HD content, but only if you have hardware protection. Otherwise, you can play 720p. But if you do downloaded licenses, then you don't have hardware protection. We want you to restrict to 480p. And by the way, if you have hardware protection, please make sure that you have HTTP 2.2 on all of your devices. Otherwise, it doesn't count, and you have to fall back to software mode and basically restrict to 720p again. That's what you have to deal with if you have to deal with studio content in a way. These are sort of the requirement sets that you have to sort of live with. How you can deal with it, there are a couple of ways to deal with this. One of them is, again, coming back to that capabilities API. It's tricky to ask your device for these properties. Specifically, HTTP is very tricky. Not only because, like, physically it's tricky, because it's an external monitor, so you can just unplug it and plug a new one, and, well, things changed. But there's literally no API that I can query upfront as of today to get the HTTP security level. So I just don't know. So it's sort of a try and error game. So that's why you can try to do this client side, but it's tricky. An alternative is actually to do the server side. And of course, you can try to do this sort of querying your device capabilities up front, but in my opinion, a very, very good workflow that can work if you have the right pieces in place on your DRM backend is you do this post manifest. So you put all your stuff in the manifest, and then you request a license, and then on the license server, you make a decision, because that's where, as I said at the very beginning, in that payload that is generated by the CDM, the device information is contained there. So now your DRM backend can actually look at that and see, oh, your device has HTTP capabilities. Your device has hardware level protection XYZ. So I give you the licenses for HD, SD, and audio, and I reject the license for your 4K content. And once that is out, you can start playback. You do this with, as I said earlier, one license request, hopefully, so it goes relatively quickly. You have all the licenses for the tracks that you are actually allowed to play. And basically, all the logic that you need in the client to make playback start quickly is to make sure that the license request is bundled and goes out as soon as possible, as soon as you have the manifest. And that allows you to do basically server-side track selection with DRM, if you want. This is a good scheme, but again, this is not working out as well. If you just use a standard Widevine proxy, you will not have that. You need custom logic, or you use a service from companies that offer that. Conclusion. There are lots of things that can go wrong. Lots of things. The good news about this is that in most of the cases, they don't go wrong in production. You figure this out during development. They're like DRM and DRM licenses and the system itself is not like dynamic in that sense. I mean, yes, you can plug in and out monitors, but that's sort of as hard as it gets. Nobody will sort of rip out the chip and put another chip and all of a sudden your security environment sort of broke down. Figuring out which algorithm is used in the future will be tricky. Dealing with security levels, hardware and software security is definitely still an issue. Output protection, as I said, there's no API for that at the moment. I think also on that there's work that's happening right now, but it's not there yet today. Filtering tracks is tricky, especially if you try to do this on the client. So server side might be a good idea there. And last but not least, CDM errors are really, really fun because you get things like this thing on the upper right corner, -2998. This comes out of white wine. I mean, everybody who worked with white wine eventually has seen that. And it's just like, yeah, I can read the docs, but there's nothing in the docs. I can Google that, and then all I find is people complaining that they don't know what that is. And up until today, I don't know. Eventually, we made it work somehow, but we don't really know what was the root cause of that underlying issue. And with that, I thank you, and if we have time, we can do questions.